What's up, all you cool cats and kittens? This is Unit 2, Modeling with Functions, and we're working on the second big idea in this unit, and last, to be honest, and that is modeling word problems. So let's get right into it. So modeling word problems. In the real world, we can often use functions or formulas to help us solve problems. So in real-world settings, we need to construct functions by translating verbal descriptions into the language of mathematics. We are learning to assign meaningful variables and symbols that will represent both independent and dependent events. Let's explore some situations where we can create a function or rule that represents real-world events. Now, when you are solving real-world problems, you will need to read the problem and process it. You have to truly understand what the question is giving you and what it wants you to find. Then you have to determine what formula or what function will be needed to help you solve the problem. And then you need to determine what you know and what needs to be solved for. So keep in mind, when asked to write a function of a variable, this means that the function only contains that variable or is only dependent on that variable, right? So for example, if I would ask you to write w as a function of g, so that means we're trying to write a formula for w in terms of g. So we're writing a function w, and you could even say a function w, right? Or, I'm sorry, I wrote f there. It should be w, right? So basically, we're finding a function w that contains g, right? So we're we're trying to write w as a function, so that's w, as a function of g. So the g is what goes into the function. So that means on the right-hand side, I could have numbers and g, no other variables. I can't have a t or an s or a q. I could have numbers like 2, 4, 6, or 7, but I also could have g's. So when you're saying, hey, write w as a function of g, it means I only want g to be in the formula. So you have to make sure you understand that. And finally, once you know what you have to solve for, you have the formula that you need to solve, you got to get your hands dirty and solve it. So in this video, we are going to look at several different examples that range in all different difficulties. Some easy, some quite difficult. So strap on, put that seatbelt on, and get ready for a crazy ride of solving word problems. Here we go. Number 1, the perimeter of a rectangular swimming pool is 96 feet. Express its area as a function of the width, w, of a side. Whew, okay, let's see here. Well, it wants me to find an area. Well, I know the area of a rectangle. The area of a rectangle is length times width. But it says to express area as a function of width, not length. So remember, it's what I just kind of said. Right now we have two. I have an L and a W. Well, I don't want two variables. I want one W, and that's W. I want one variable, W. So I got to figure out, how can I get rid of the length? And that's where I got to put my thinking cap on. We were told that the perimeter, as I walk around this rectangle, swimming pool, is 96. So that means, right, if I think of the length as these values and the widths as these values, as I walk around the swimming pool, I know that there are two widths and two lengths. So if I walk around, that's an L plus a W plus an L plus a W, two W's and two lengths, two W's and two L's. And I know the perimeter is 96 because they told me that. So what I could do is I could solve this formula for L and plug it in to replace that L. So let's see, let me solve for L. So I get 96 minus 2W equals 2L. Divide everything by 2, and I get length equals, let's see here, if you need a calculator, feel free. 96 divided by 2 is 48. Negative 2W divided by 2 is negative W. So now I know, based on the perimeter, that the length is 48 minus W. So now I could come back over here. I could replace the L with what it equals, 48 minus W. Don't forget to times it by the width, because remember, area is length times width. And now I created a function that only contains the width. And I can even go ahead and distribute the width, and I get 48 minus W squared. So here is a formula that is a function area as a function of only W. So again, this is an example of exactly what I was talking about, creating a function that only contains that one variable, but having to use these two concepts of area and perimeter to figure that out. So I think that's actually probably like a level 1 problem. That's pretty basic, not overly difficult. All right, let's step it up a bit. So the volume of a right circular cone is 1/3 pi r squared times height. So if I have a cone here, like a 3D cone, sorry, that's a terrible drawing, but we have the height, we have the radius of the base, r, and the volume of a cone is 1/3 pi r squared times h. Okay, so if the height is 3 times the radius, express the volume as a function of the radius r. So I already know the volume. The volume is 1/3 pi r squared times h. But remember, I want to express the function as only the radius. I don't want this h. So I need to replace the h. Well, what do I replace the h with? Well, it said that the height is 3 times the radius. So I took this word, or I'm sorry, this sentence in English, and I converted it to math. Is means equal, so h is 3 times the radius. So now I can replace h with 3 times r. So volume equals 1/3 pi r squared, but instead of an h, I'm going to type in 3r. So now I just got to clean this up. Let's see here. R squared times r is r cubed. The pi is not going anywhere, so I'm going to leave the pi right there. And 1/3 times the 3 is just 1. So they kind of reduce. 1/3 times 3 is 1. So essentially, I get pi r cubed. So the volume as a function of only r for this particular cone is pi r cubed. All right, now they want me to use my formula. Oh my gosh, crazy. Find the volume of a cone that has a radius of 1.3 feet. So volume equals pi times 1.3 cubed, and if you plug that in, you get 6.902 cubic feet. So volume is in cubic feet there. So the volume of that cone is 6.902 cubic feet. So another pretty simple problem, I think, especially when I gave you, now I wouldn't expect you to remember this, I will give you that formula for the volume of a cone. All right, actually, before we get into number 3, let's talk a little bit about business. So in the business world, we are concerned with sales, costs, revenue, consumer demands, and profit. And revenue R is defined as the money received for a sale of X units sold at a retail price P. So the revenue is how much money a company brings in by selling a product, where the revenue equals the price of that product P times how many units they sell. Easy. So if the price of a toy is $5 and you sell 100 of them, 5 times 100, you're expecting to make a revenue $500. But the law of demand from economics tells us that with the price, the units are related. Price and units are related. Specifically, as one increases, the other decreases. So if you increase the price of a product, you're probably not going to sell as many items of that product. If you decrease the price, you'll sell more items. Simple supply and demand. All right, so let's dive into some problems that utilize this idea of business. All right, this is a really good problem, and I think that it just takes a lot of common sense, and you'll figure it out. So the demand for tickets to an NSYNC concert, hopefully you remember who NSYNC is, like one of the greatest boy bands ever. But anyway, they're not as popular anymore, so maybe they don't catch as many people at their concerts. But especially with COVID, probably nobody goes to their concerts. But I digress. Okay, so the demand for tickets to an NSYNC concert is given by the price equals 265 minus 0.04x, where P is the price of a ticket and X is the number of people going to the concert. So again, X is the number of people going to the concert, P is the price of the ticket. More people go to the concert, the price drops. Less people go, price increases. All right, so first question is pretty straightforward. What price would provide an attendance of 5,000 people? So again, P is the price that I'm looking for, and X is the number of people that are going to attend. So I'm going to type in 265 minus 0.04 times 5,000. Utilize your calculator, unless you're simple to do that math in your head. And we get a ticket price of $65. So if tickets are on sale for $65, we will probably get an attendance of 5,000 people. Okay. What is the total revenue at this ticket price? Well, remember, revenue is simply the price per item, $65, times the number of people buying that item, 5,000 people. So 65 times 5,000 is a total revenue coming in of $325,000. So if NSYNC sells their tickets for $65, they're expected to get 5,000 people. 65 times that 5,000 people is going to net them a revenue of $325,000. All right, so now they want us to write the revenue function as a function of the attendance X. So this is where we got to think about what I mentioned way back in the very beginning. We want a formula for revenue that only contains X. Now remember, the generic formula for revenue is price times X. But we don't want two variables, we want only X. So I need to replace this P with something, and oh my gosh, there it is. The price is 265 minus 0.04x. So that means if I only want X's, I'm going to replace the price of a ticket with the formula I was given, 265 minus 0.04x times X. Don't forget to multiply by X. That was, again, part of the formula. And then, of course, I could distribute that X to get 265x minus 0.04x squared. So if I know X, the number of people that are going to attend the concert, I could plug that into this formula and I will get my revenue. Easy. Hopefully you understood that problem. But again, you had to think a little bit. So that might be a level 2 problem. Not overly difficult, but makes you think. All right. Now let's really step it up. I love this question because it really puts everything about business into one problem. So you really got to think about this one. A purse designer has a fixed monthly cost of $15,406 and a variable cost of $24 for each purse produced. So this means in any given month, the cost to sell a purse, just the cost to produce the purse, it's going to cost them $15,406 in fixed costs. That might be to pay their employees, to pay for the lease on a warehouse where they make the purses. Maybe that's to pay for the supplies, whatever, right? There's a lot that goes into making purses. And then again, it also costs $24 for each purse produced. Again, purses contain leather, metal, zippers, whatever. You get the idea. And the purses sell for $130. All right, so write an equation for the profit as a function of X. All right, now this is where we really got to make sure that we think like a business person. All right, profit is all of your revenue minus your cost, right? Revenue is how much you bring in. Cost is how much it costs you to make that product. So your profit's how much money you get to go home with. So that's, again, your revenue minus your cost. So let's talk about revenue. The revenue is the price times how many units you sell. Well, we already know our revenue is $130 for each purse. So that's 130x for my revenue. The cost to create a purse is a fixed cost of $15,406 plus $24 per purse sold. So that's going to be my cost. So my profit as a function of X is going to take the revenue, 130x, that's $130 per purse, minus the costs. Each month it costs me $15,406 plus 24x to produce the said purse. So now putting all this together, distribute that minus sign, I get 130x minus $15,406. Again, that makes sense. It's negative because it's cost. Minus 24x. Again, makes sense. It's negative because that's what it costs you. So all I got to do is combine the like terms here. 130 minus the 24x is 106x minus $15,406. So this right here is my profit function. If you know how many purses you're selling, plug it in. So if you only sell one purse, you are not making any money. You're going to make negative profit because you spent way too much in overhead and you only sold one purse. So you need to sell a lot of purses in order to start making money. Which leads me to the next question. How many purses should the designer produce and sell each month to break even? Well, we've already determined that the profit formula is 106x minus 15,406. And if we break even, that means we went home with zero profit. We didn't lose any money, but we didn't make any money. That's a break-even point, making $0. So all I got to do is plug in 0 for the profit. I broke even, and I got to solve for X. So I'm going to add the 15,406 over. I'm going to divide both sides by 106. And X is, grab a calculator if you need to, 145.34, which is approximately 146. Always round up, because if you actually round down, then you're actually going to be cutting yourself a little bit short. So I need to sell 146 purses to break even. If I sell 146 purses, I will break even. Awesome. Okay, any more selling, I make profit. Any less, I lose money. All right, so finally the last question is, what is the total revenue at the point where the designer breaks even? So if the designer does break even, only selling 146 purses, what is their revenue? Well, remember, revenue is simply the cost of the purse times the number you sell. So remember, we're selling these purses for $130. So 130 times 146 is a profit, or excuse me, not a profit, a revenue of $18,980. So if I sell 146 purses, I will make my revenue. I will make $18,980. But again, remember, all of those purses cost me money. So that is, of course, why I'm breaking even. Hopefully that problem makes sense. That's a good business problem. I mean, that is how the business world works. All right, let's get into a little bit more mathematical problem, right? So it's still a word problem, but this one's much more function-based, mathematics-based. All right, and this is actually a really famous problem from calculus. All right, so let's explore a point P, x comma y, right? That's what points are, x comma y, on the graph of x squared minus 3. So this is a function, x squared minus 3. So if I plug in x, the y value is x squared minus 3, right? Because isn't f of x y? So if I know x, then y becomes x squared minus 3. So for example, if x is 1, then I have 1 comma negative 2. So there's my point. All right. Now, our goal is to find an approximation of a point on the graph that is closest to the origin. So it could really help me if I were to maybe take a quick look at a graph. So hopefully you guys can simply use what we learned last unit with transformations, and we could make a quick axis here. And this would be a parabola that's down 3. So 1, 2, 3, a parabola that went down 3. And so it's a very crappy looking parabola, but you get the point. Now, the origin is right here. So basically, I want to figure out what is the closest point to this origin. Is it up here somewhere, or is it down here somewhere, over here? Where is the closest point? So this is where we need to do exactly what the question says. It says express the distance d from any point P to the origin as a function of x. All right, so let's just make, the origin is obviously easy. The origin is 0, 0, and I'm going to make up a random point, and I'm going to call it x, y. But remember, we know that better as x, x squared minus 3, because y is f of x, and f of x is x squared minus 3. So now you have to remember distance formula, because that's distance, right? I hope you guys remember the distance formula. If not, I'm going to give it to you right now. So the distance between any 2 points is the square root of subtract the x's squared plus subtract the y's squared. All right, so if my 2 points are 0, 0 and x comma x squared minus 3, I'm going to do, let's see here, let's subtract the x's. That's going to be x minus 0 squared. So here's x minus 0 plus, now my y value, again, I could say y, but I want a function x. I don't want any y's. I want just x. That's what we mean when we say write it as a function of x. So again, y is x. It's a function based on x, and that's why it's super important you understand that y is x squared minus 3. So I'm going to replace y with x squared minus 3 minus 0, because that's the other y coordinate. So the formula for the distance is the x value minus the x value, x minus 0 squared, plus the y value, x squared minus 3, minus the y value, 0 squared. So now if I just kind of clean this up, I get x squared. Obviously, x minus 0 is x squared is x squared. Plus, now I get x squared minus 3 minus 0, obviously I don't need to worry about, squared. And now I just have to square that out. So I have x squared plus, let's see here, if you need to do some dirty work, you know how much I love dirty work. So come to the side, x squared minus 3 times x squared minus 3. That's going to be x to the 4th minus 6x squared plus 9. And finally, I can clean this up a little bit because I can combine my 1x squared with my negative 6x squared. And I get x to the 4th minus x 5x squared, plus 9. So there is a formula right there. Crazy formula, but that is a formula for the distance from any point P to the origin written as a function of x. Pretty cool problem. All right, let's keep doing more with this. So now it says use a graphing utility to graph the function d for x greater than or equal to 0 and find the values of x where d has a local minimum. Now this will give the points on the function or on the graph of the function x squared minus 3 closest to the origin. And then it says actually find the point closest to the origin. All right, I'm assuming at this point you're probably a little bit confused. So let's track back. The formula for the distance between the origin and any point on our function, we found out to be x to the 4th minus 5x squared plus 9. Giant square root around all that. Okay, now what you have to understand is that this function right here represents x as the x coordinate of any point on this function, and the output is the distance between the origin and the point. So for example, if I were to pick this point right here, x would be the x coordinate of that point, maybe 2.2, and d would be the distance to that point. That's what d would be. All right, so what I could actually do is I could graph this function. I could graph this distance function, and the minimum value, the minimum of this distance function would be the minimum, the shortest distance. And that's what I'm looking for, right? I'm looking for the point that is the smallest distance from the origin. So again, I'm going to go ahead and grab my graphing calculator. And I'm actually going to use Desmos, because to me that's a much prettier looking graphing calculator. And in Desmos, I went ahead and typed in the formula, distance, d, equals the square root of x to the 4th minus 5x squared plus 9. And I get this graph. Now this graph represents x, that is the x value of my function, and d represents the distance. So I see that there are two mins, which actually means there's two answers, and that should make sense here in a minute. Now, please understand that the x values is 1.581. The y value is the distance, the shortest distance, because again, these are the mins, right? So now if I go back here, let me write this down. So let's use the one on the right. So x was 1.581. The distance was d, 1.658. So if I go to my graph over here, let me erase what I already drew there, and let's actually pinpoint this. So an x value of 1.58 would probably be right about here. That means the point is right around here. This point right here is the point that is closest to the origin 0, 0. Now, if you go back to that graph I made, you notice that there was a second minimum. They were tied. And the other x value was negative 1.581. And that should make a lot of sense, because if positive 1.581, again, about right here, and negative 1.581, about right here, that would make sense that those are both equal distance and the shortest distance to that origin. So that means the functions, the x value of my function, the point I'm looking for, is 1.581. Now to get the y value, I got to go back to my function. Remember, this was the distance formula. So the distance, that's the red line here and the red line here. The distance is 1.658, but I want the actual y coordinate of this point. So now that I have the x coordinate, I got to plug that in to get my y coordinate. So I'm going to use my calculator. I'm going to type in 1.581 squared minus 3, and the y coordinate is negative 0.500. If I round that, negative 0.500. So that is this point right here. And again, the same point over here would be negative 1.581. And because of symmetry, it would have the exact same y value, 0.500, negative 0.500. Oh, boys, this is a tough problem, right? You really got to really hold on tight for this one. So let's kind of look at the two graphs here. So first we have our parabola. And what I wanted to find was the shortest distance between the origin and a point. I wanted to find what point is absolutely the closest to the origin. So close is a measure of distance, right? Distance. So that's why I first needed the distance formula. So at first, I didn't know what the answer was, so I had to keep things generic. I had to keep x as x, and I had to find a formula for the distance that involved x. And that's what I did. That was the first steps I did. Then I graphed that distance formula, which is here in red, and I found the two minimums, which would represent the minimum distance, the shortest distance. And I realized that there were two answers, 1.581 and negative 1.581. So that was this point right here, and again, the same corresponding point right over here as well. That's the negative 1.581. And then again, I needed to find the actual y value of that point, and that's where I took the 1.581 and plugged it into the formula for y, because remember, y was x squared minus 3, and that's how I got my y coordinate. So the closest point to the origin was 1.581 comma negative 0.5. So what a word problem. The question was essentially, here's a function, and what point is absolutely the closest to the origin? And it took me a lot of work, a lot of really good work, but I was able to find the point that is the closest point to the origin, 1.581 comma negative 0.5. Boy, that was a lot of work. I might want to watch that again. All right, that's it for right now. We are going to look at several more problems in part 2 of this topic. So please stay tuned. Please watch the next video as well that covers even more really great word problems that we need functions to solve.